Okay, thanks for having me here. Thank you everyone for tuning in. So I'll be talking, my official title is Multi-Messenger Probes for Fundamental Physics, but I'm going to start with a bunch of caveats. Hold on, I'm having trouble, just give me a second. I'm having trouble sharing, getting out of. It's not letting me advance my slides. Just give me a second. I don't know. I tested all of this. Okay. I'm going to try sharing again. Okay. There we go. Okay. So there are a number of caveats. First, by multi-messenger here, I mean basically gravitational waves. I noticed that in this meeting, there are not that many talks about ground-based gravitational wave detection, so I'm really going to focus on gravitational waves and LIGO Virgo detections. So I apologize, I'm kind of putting neutrinos and cosmic rays and the rest to the side. By fundamental physics, I'm going to include astrophysics and cosmology. There's just so much going on. I'm not even going to attempt to do a broad review of everything that's going on in this space. I'm going to just focus on some of my recent work, which I think is kind of representative of a lot of what's going on and a lot of the excitement. So, an alternate title is, what do we learn from combining gravitational waves and photons? And that's really going to be my focus. I'm going to give you a few sort of snapshots of some of the things that we learn when we combine these things. Okay, so just to give you a sense of what's going on, here's some of my recent work on this is sort of gravitational wave astrophysics generally, and I'm going to highlight some of these papers in this talk. The first set has to do with the equation of state. Then there are some papers on standard sirens, which I'll discuss at some length. There's also work on gamma ray bursts. There's some work on the stochastic background. I'm not going to have time to talk about that. There's a lot of work on population parameters, populations of black holes mostly. So those generally don't have counterparts, so that's not relevant to this particular talk, but it's been a huge area of research in gravitational wave astrophysics. I might, right at the end, talk about binary host connection. Another thing I'm not talking about, so these in addition to these papers, there are lots of LIGO papers, and I wasn't going to discuss any of the LIGO results per se. So I might mention a few of the more recent results as I go along, but that's not going to be my focus. This isn't really a LIGO talk. Okay. So any sort of discussion of gravitational wave multi-messenger astronomy basically starts and ends with 1708-17. Of course, this is the event. It's still, the most amazing thing I think that's occurred in astronomy. I'm a little biased, but it really is an incredible event. And needless to say, just at the highest level, this was the first time that we got to have gravitational waves and photons from the same source, and that lets us do all sorts of different things, and that's going to be the focus. When you have gravity, you're sort of probing the gravitational field, the large-scale bulk motions. The light is giving you a completely different probe, atomic transitions and more astrophysically oriented. Combining those is very, very powerful. So that's the general theme. Okay. Again, just to get everyone situated, I'm not sure if you can hear that, but this is the gravitational wave strain at the bottom, and then the gamma ray burst. And so the top is just what we detected in gamma rays. The bottom is what we detected in gravitational waves. And the main thing for right now is to notice is that the gravitational waves end, and then about 2 seconds later, there's this burst of gamma rays. Okay, so the first, easiest, and in some ways one of the most profound results that come out of this from the point of view of fundamental physics is you can ask the question, do the gravitons and photons, did they travel at the same speed? And the answer is basically yes. And that's, you can see that from this slide. And the point here is you might think, well, 2 seconds is a long time. Photons can go a long way in 2 seconds. But these photons and the gravitational waves have been traveling for 100 million years, and yet they arrive within 2 seconds of each other. And that implies that if there's any difference in their speed, it's very slight, and it's on the order of 1.10 to the 15 or less. So that's an extremely tight bound compared to essentially having no bound before. That's a major advance in the field. And that lets us answer this very fundamental question, which is, do they travel at the same speed? The answer is yes, they do. And this is a major development in the theoretical regime, and this, as you probably know, rules out many modified gravity theories. It's a very powerful, and it's a classic multi-messenger result. We have gravitational waves, we have photons, we just compare. Okay. Now, there's another aspect of this, which you ask, it's just slightly different focus, very similar approach, which is you can also ask, do the gravitational waves and the photons see the same universe as they're traveling? And what I mean by that is you could imagine, and there are plenty of theories where you modify, in essence, you modify the universes that gravity sees compared to electromagnetic fields. You can add extra dimensions or scalar field. There can be couplings that cause, in effect, the universes to be different. And if that's true, then you might imagine that gravitational waves, for example, can leak into the bulk. It's as if there are these higher dimensions and they leak out. And that would cause the gravitational wave sources to appear dimmer than they really are, or you would infer the distances to these sources to be farther away than they really are. And 170817 lets us test this. We have a distance from the electromagnetic side. You can think of it as kind of the electromagnetic flux, and then we have the gravitational wave flux, and we can compare them and see, are we losing gravitational wave energy? So this is something we looked into, and there are ways to express this in terms of the number of space-time dimensions. It's kind of a cute way to sort of characterize what's happening, and then you can just fit directly for the number of space-time dimensions. So this is work I did. This was led by Chris Pardo, who was a graduate student with Dave Spergel and is now a postdoc at JPL. And he showed that when you combine all this data, you end up with a measurement of 4 space-time dimensions, 3 plus 1, with some errors, but it's a sort of a direct measure of the number of space-time dimensions out to tens of megaparsecs, out to cosmological distances, showing that they actually go through the same universe. You might not be surprised that that's the case, but this is an actual measurement showing that this happens. You can also then take a slightly different approach and instead phrase it as the running of the Planck mass. A lot of scalar tensor theories end up having some running as part of what part of the modification. And so you can characterize that. And if that's happening, then again, you're going to have impacts on the gravitational wave flux that you can measure. And so we analyzed this. This was work led by Maka Lagos, who's a KICP fellow at the University of Chicago. And we showed that CM here is kind of the parameter that governs the amount of running. 0 is consistent with no running. And we showed that so far everything's consistent with 0. It's not a fantastic constraint. It's just the very first time this is being done. Nonetheless, that's what you end up with. All right, so do gravitons and photons see the same universe? So far, the answer is yeah. Okay, so next. So from now on, I'm just going to assume GR is correct and go from there. I'm a relativist, so this is the way I like to approach things. So now I'm just going to give examples of once you assume GR is correct, you couple with photons, what can you learn? One of the classic examples is neutron star equation of state. And the point here is that you can measure properties of the neutron star. They're embedded in the gravitational wave waveform. So if you measure the waveform carefully, you'll see the neutron star gets deformed, and that causes phasing in the waveform. And you can measure that, and you can infer what the properties are of that neutron star. And that's a fundamental, aspect of nuclear theory. So it's something we'd really like to be able to measure. Now, if you couple that with maximum masses of neutron stars from pulsars, electromagnetic data, or recent nicer data, you can then, within the space of possible equations of state, further constrain things. And here's a plot, an example of this, where you take the chiral EFT model, which is a model for the nuclear equation of state, and then you can test what sorts of equations of state are consistent with the data. Okay. Another thing you could address is you could try to ask the question, how does the universe make binary neutron stars in the first place? How do we get the rate of binary neutron stars to work? This is actually a big question in astrophysics right now. We don't know how the universe manages to make binary neutron stars that are frequent enough. These are binary neutron star mergers, such that it's consistent with what LIGO is seeing. And there are a lot of different ways to characterize this. I'm not going to go into the details, just to say that one example of a way to constrain this is to correlate the host galaxies with the binary neutron stars themselves. So we're going to get binary neutron star mergers from gravitational waves. For each of them, if we can get an electromagnetic counterpart, we can find a host galaxy. The host galaxy will have the properties of the host galaxy will give us important clues as to how the binary neutron stars were formed. And there are a lot of details here. I'm going to skip that for now. I'm just going to say we have one example of this binary host connection, which of course is 170817, where we know what the host galaxy is, this NGC 4993. And just that one galaxy already gives you some information of the properties of how these binary neutron stars are made. It gives you some sense of the time delay, how long it took from when the stars happened, when the stars were born, to when the binary merged. And the indications are it was some number of gigayears, and that's quite interesting. Okay, this is an example of combining gravitational wave and electromagnetic data. So finally, I'm going to spend some time on the Hubble constant, and fortunately, Adam just laid it all out and gave the perfect motivation for maybe having an alternate way to measure the Hubble constant, something sort of complementary. And so I'll just spend a few minutes on that just to wrap up. And so the main point here is that gravitational waves provide this very natural, scale-free, kind of beautiful way to measure distances. And that's through these things we call standard sirens. And the idea is that black holes are very simple. Black holes are just defined by, first approximately just a mass, and if you really want to complicate things, you can add some spin, charge is probably irrelevant, and then that's it. And that fully defines your system. And so you really, from first principles, from just GR, can understand what the gravitational wave signal should be. Not all the way through merger, but certainly the in-spiral is very, very simple. And so if you observe that in-spiral, you can reverse engineer and directly measure the distance to the source. So it's an absolute distance, no distance ladder, you just measure the distance to the source. The problem is that you don't get a redshift, so you need some independent measurement of redshift. And the easiest way to do that is to have an electromagnetic counterpart. So if you have gravitational waves and you have photons, then you have some hope of measuring redshift and distance and playing this game. I'll skip over this. And just to kind of really boil it down, if you look at the bottom here, on the left side, the recession velocity or redshift, however you want to characterize it, that can come from the electromagnetic side. The distance comes from the gravitational wave side, and you can solve this to get H. Okay, there are two general ways to do this. One is to have the redshift come directly from the electromagnetic source. So for example, like 170817, when you have a host galaxy and you can measure its redshift, there's another way where you do the thing statistically. And for now, I'm just going to focus on the counterpart case, what we call the bright siren case. And in this case, the gravitational waves provide the distance, the photons, you can measure the redshift of that galaxy, and now you have a point on the distance redshift curve. So this is a very clean and direct way to measure things. The only problem is that you actually need an EM counterpart, and you need an associated redshift. And as you probably know, I am not announcing a new LIGO detection right now. This is the only one we have. 170817 is the only data point so far. But for this case, you can actually apply this approach. And in some sense, 170817 was, the poster child. It's like the perfect way to do this. It was very high SNR. We got a very good measurement of distance, relatively speaking, for gravitational wave sources. It had this optical counterpart. We got a redshift. We could go forward. One thing just to bear in mind is that 170817 was in some ways too good. The host galaxy was too close. Peculiar motions start to be a problem. That's why it was so loud. It was just a little too close for the standard siren stuff to work smoothly. And so there were lots of complications and sorts of things that can keep you up at night, virial corrections and bulk flows. And now, as we get farther out, these should become much less important. But all of this had to be accounted for. When you do all this work, you end up with this plot. I still just love this plot. I can't believe this all actually works and it all happens. And so this is just the posterior on the value of the Hubble constant. And the curve is what you get from 170817. This is just a straight standard siren. You have one, there's no distance ladder. You have one source. With this source, you measure the distance in gravitational waves. You have the redshift, you get this plot with the corrections I was talking about before. And you can see the bands. These are kind of older bands for CMB on the left in green and Adams results for the H0 on the right. And these have now tightened, and so the discrepancy is actually more severe. And okay, we don't have it's very broad. We're kind of consistent with both. But this is the very first data point, and it's just amazing that we're even on the plot, and it bodes well for the future. I should just mention that there's also a distance inclination degeneracy in these sorts of measurements. And what that is that it's a very good measurement of distance, but it's not a perfect measurement of distance. And part of the reason for that is that if you take a binary and you view it face on, it's louder, and therefore it could be farther away and look similar to a binary that's closer to edge on and closer to us. And so that distance inclination degeneracy causes that wider bump in this plot. And so if you could break that, you can do better. And there have been lots of attempts to do that. And so, for example, you can use astrophysical measurements, jet breaks, try to do modeling of the jet to infer what the inclination is of the binary. If you can measure the inclination, then you improve your standard siren measurement. And then you go from this orange curve to the blue curve in this plot. And you can see that it gets narrower, which is great. I'll just remind everyone, and Adam's entire talk is kind of a very powerful example of this. This game, at the end of the day, is all about systematics. In this case, you take kind of this pure GR approach, and now you're putting a lot of astrophysical modeling into it, astrophysical measurements. And so although you certainly improve your constraint, you also potentially introduce systematics. And so that's something that you have to do very carefully, very deliberately. Okay. I think I'll just spend a few minutes on the statistical method. So what I talked about just now is the counterpart standard siren method, but you can also approach this statistically. And in that sense, you say, well, okay, maybe it's a binary black hole. I get a very good distance, but I have no idea which galaxy hosts the black hole binary. The black holes are dark, and so I don't have a counterpart. Well, then what you can do is there's some number of possible hosts within the volume where your gravitational wave source occurred, and each of those is a possible redshift, and you can use all of them as measurements of H0, and you're going to get some broad distribution of possible H0s. But if you do this many times, it should converge on the right value. And this was actually the original method suggested by Bernie Schutz in his paper in 1986, which is really the paper that defined standard siren science. And What's great about this is you can do it for all sources, including binary black holes. But the problem is that there are many galaxies in the universe, and so this ends up converging very, very slowly. In work led by my grad student, Maya Fischbach, we applied this method to 170817, pretending we didn't see the galaxy, sort of closed our eyes, and then just took galaxy catalogs instead of the real NGC 4993 and did this approach. And we found that it actually worked pretty well because it turns out 4993 is embedded in a group, and that group's at the right redshift, and so you get more or less the right answer. And so here's the sort of H0 measurement you find. And the pink line, the highest peak line, is what we had from the counterpart. And then if you would just use all the galaxies, you get the orange or the green. There are a lot of subtleties in how you can weight the galaxies different ways. If you think that it's more likely to be in a big galaxy, then you might weight, by stellar mass, and then you select some galaxies over others. But what you see generically is you do get a measurement. In this particular case, it happens to peak in the right place. It's just not as good. Okay. So what about the future? As we go forward, we're going to get more and more of these sources, and these measurements should improve. And so this is supposed to give you some sense of how quickly things improve. On the left, you have counterpart cases. Each of those are relatively narrow, 10 or 15%, and they start to converge. For the statistical case, it's a much, much slower convergence. And that's kind of summarized in this plot. And this is work led by my former student, Xinyu Chen. What we show here is that, what we show here is that in about, it's probably something like 3 years or so, we should get to the few percent level. But this depends a lot on the actual rate of binary neutron stars, and in particular, whether all these binary neutron stars have counterparts. And so if you've been following along, we had 170817. That's the only one with a counterpart so far. We announced one more at the AAS meeting, a sort of bigger binary neutron star, but no counterpart. And that's where we are right now, as far as announced events. So, we're not, we need samples of these, and our sample is accumulating somewhat slowly so far. Adam actually sort of emphasize this as well. The point here is that the Hubble constant, not only is there this Hubble constant tension, but the Hubble constant, by really nailing it down, it helps you constrain all the cosmological parameters. If you really want to understand dark energy and measure the equation of state of dark energy, it helps to have a very accurate measurement of the Hubble constant. And that's something that you can see here. Okay. So I think I'm going to use my remaining time to focus on a new way to measure the Hubble constant, a new sort of standard siren approach. And I think it kind of elegantly shows the power of gravitational wave astrophysics and the way, how quickly this field is moving, and the opportunities there. And so this starts with a sort of black hole populations observation, which is that Maya Fischbach a few years ago, she noticed that we're missing big black holes. And so the biggest black hole that we've seen in gravitational waves is on the order of 30 solar masses, like 150914. And that's pretty big compared to the sun, but the gravitational wave detectors are actually quite sensitive to much bigger black holes. The bigger the black holes, if you had a 50 solar mass black hole, that's extremely loud. We can see that much farther away. We have a lot more volume that we're sensitive to. So the fact that we haven't seen any 50-50s or 70-70s, that's surprising. And we turn that into kind of an analysis to say, there's very strong evidence. The way we phrase it is the absence of evidence is evidence of absence. We're quite confident that those black holes, the bigger ones, are missing. It goes up to 30 and then seems to cut off. And this is kind of an example of this, where you can see that the maximum mass, thank you, 5 minutes. The maximum mass is on the order of, maybe 45 solar masses. So Okay, so that's very interesting. That has to do with period stability supernovae. That's its own thing. It's something, it's completely fascinating from an astrophysics perspective. But what we realized more recently is that that also gives you a feature. And if you have a feature, you can use that to infer information about the Hubble constant. And so you can effectively use that feature to measure redshift. And this is, work with Will Farr, who's at the Flatiron and at Stony Brook. And he, in this, we utilize this feature. You can think of it as an emission or absorption line. There's this feature cutoff, which is the maximum mass. As you go to high redshift, that feature redshifts. So the location of that feature tells you the redshift. You can measure distance from standard sirens, and you can end up doing a very good measurement of not just the Hubble constant now, but h of z. It's a direct measurement of the expansion history of the universe. And for future surveys, when we talk about, say, 5 years at advanced design sensitivity, which should start in a few years, or A+, which is the next generation, which starts around 2025, at that level, now you're getting percent level measurements of the full expansion history of the universe out to, redshift 1 or so. So it's extremely powerful if you understand this feature and if it doesn't involve and have systematics. There's a lot of details here, but it's, in principle, it's somewhat like BAO, only it's an absolutely nailed down feature. Okay. So there's a lot of promise here. As Adam would be the first to point out, the devil is in the details, and it's all about systematics. There are lots of systematics, potential systematics. In the counterpart case, I would claim, at least so far, this is all reasonably clean and understood. Probably the greatest concern, the greatest systematic that right now that we worry about has to do with the actual calibration of the instrument. How well are you measuring your amplitude, and could there be a systematic in that? And to measure H0 to 1%, you have to have your calibration. You have to know when the mirror moves that you understand how much it's moved to 1%. And that's hard to do, and there are different ways that the ground-based detectors are approaching this. The standard calibration is called a photon calibrator. You shine light on your mirror. If you know how bright your laser is, you know the radiation pressure, and you can calibrate what's going on. And that's the way things are happening now, and it's probably good to somewhere a few percent, maybe 5% or so, and it's improving. So that's something where we expect to get to better than 1%, but it has yet to be done. There's a very interesting alternate way to do this using what's called a Newtonian calibrator, which is basically you spin a dumbbell, and then you can use just Newton's force law to figure out what the varying force on the mirror is, and you can calibrate the response that way. And that's, right now it's at 10% level, but in principle, this could be extreme. This could be done very, very well, and this could also get to the percent level. It'd be very good to sort of cross-check that with the photon calibrator. So there's a lot of progress there. I'll just mention some work I did with Reed Essick, who's a postdoc here at Chicago, where we calibrated the detectors using 170817. If you assume GR, you know what the waveform should look like. And so if you assume that was the real waveform, you can actually calibrate the response of the detector. So we've gone from just hoping we have a detection to actually being able to constrain the performance of LIGO based on the observation of 170817, in part because it was so loud and clean that we could really do this over many, many cycles. It's not a great calibration. It's 20, 30%, but the fact that it can be done at all is kind of mind-blowing. Okay, so I'm just going to wrap up. So the point here, this is kind of a whirlwind tour of some of the results in gravitational wave astrophysics and cosmology, focusing on this point that now that we have gravitational wave sources and light, there's a whole new set of questions that we can ask and address. Right now, LIGO's off. All the detectors are off. And they were suspended slightly early. We've announced a few detections. We'll have more, still analyzing the data. We'll have some summary of the data soon. Then we'll turn back on sometime in the hopefully not too distant future. And then we'll see what happens. It's really been incredibly exciting, and still have a long way to go. Okay, I'll end
there. Thank you, Daniel, for that very interesting talk. We have a few minutes for questions, and I'm going to the Q&A box where a few questions have been submitted already. I'm sorry if I sometimes may not pronounce your name correctly, but I'll do my best. Question from Natalia Tenorio Maya asked, could you tell us if by measuring the spins of the neutron stars would help us understand how binary systems are formed?
Yes, yeah. So measuring spins is extremely helpful. The focus so far has really been on the black hole side, so I'll just give a quick description of that, which is, so in many cases, most formation mechanisms, you expect the black holes to spin. If you're being formed in a sort of in situ binary, what's called a field binary, just you had two stars, they evolved, they formed two black holes, and those merge. In that case, the spins in general are aligned. If the other model for formation is that you're formed in a dynamical environment, like a cluster of stars, and those the stars form black holes. The black holes are exchanging pairs. You can have this even hierarchical formation where you have black holes that merge and generate more black holes that then merge. In those cases, in general, the spins are random, isotropic. And if you can tell the difference between those, then you get a lot of information about which channel it is. So that's something we really want to measure. LIGO doesn't do a great job. The gravitational-wave did LIGO and Virgo don't do a great job of measuring spin alignment yet. We're very insensitive to spins in the plane, but that's something we're working on. All of this also applies to neutron stars. And so if you have a model of neutron stars that does it dynamically, then you would expect the spins to be kind of random. I will point out that in general for neutron stars can't spin nearly as fast as black holes. They rip themselves apart. And so it's just a harder measurement overall.
Okay, thank you. We have about 2 minutes, so I'll try to get in a couple of more questions. The next question is by Peter Denton, who asked, when doing the statistical method to estimate H0, does this method carry an underlying weighting by the redshift distribution of the catalog? Can you discuss how this is accounted for?
Yeah, so that's a great question. So yeah, so in that case, you're using a catalog. The catalog exists in redshift space, and you have to understand particularly the completeness of that catalog in redshift space. And so there's a lot of work doing that. It's very hard to characterize that. Then you have an H0 prior, which then turns that into your distribution in distance space, which is the relevant one to compare to the gravitational wave data. So there are a number of steps along the way. You have to be extremely careful in the way you do that. It's taken a lot of work. We've written a number of papers really kind of laying out how to do this carefully. We think we have this under control, but you have to understand your catalog. And in particular, you have to understand possible systematics in the redshifts in your catalog. And it turns out, especially at low redshift, the redshift estimates are quite poor and unreliable and may have embedded systematics. And that's actually, I would claim right now, maybe the hardest part of this.
Okay, very good. I'll just ask one more question and you have about a minute to answer. For your, by Yatan Buch, I presume, I hope I said that incorrectly. For your projections with the standard sirens plus EM counterparts, do you marginalize over the inclination, or are these results assuming some optimistic model for source galaxy identification?
Yeah, okay, so great question. So in everything I've presented, we've marginalized over inclination. So we've assumed the inclination is random and we marginalize over that, except for the one plot I showed for 1708-17, where we used the electromagnetic measurements, the kind of radio measurements to constrain the inclination angle. And then in that case, we took that as priors to improve our posteriors on H0. But for the rest, we just marginalize, which I claim is, given that I don't really trust any of the modeling yet, that's kind of the safe thing to do, but it causes a much broader estimate for H0.